We now start discussing the equations that describe an electric vehicle. And these equations are based on some work in a textbook called Fundamentals of Vehicle Dynamics by the SAE. They're fairly standard kinds of equations for modeling vehicles of any sort, but of course we adapt them to the electric vehicle need when we get to the power that drives the load itself. The equations here are ultimately used in a set of MATLAB code that's an appendix to this chapter of notes, and it might be valuable for you to follow along with that. Over the next two sections we'll describe first the vehicle and then the load, the vehicle range calculations, the battery part of it. But there's two programs in the appendix to this chapter. One is Setup Sim Vehicle, that sets up parameter values for the simulation, and then there's Sim Vehicle, which is the code that executes the equations. So you might look at Sim Vehicle, and even though maybe all the details won't be apparent, you can at least tag in the code where we're talking about that equation in the notes, so that later on, after you've listened to both sections of the lecture recording and gone through a section of notes, you can compare it with the code, and there should be a one-to-one correspondence in what you see. In any case, we start out every time interval in the simulation by computing for that time interval what the desired vehicle acceleration is. And we do that by taking the desired speed from the profile of speed versus time, and we subtract the present actual speed, and that's a velocity difference in meters per second. And if we divide that by the sampling period, which in our case is a 1 Hertz sampling period, we get meters per second squared, which is an acceleration. So that's how we get the desired acceleration over the next time interval. Notice I put units on everything because units are not always standard. I try to use standard metric units here. Of course, different literature will use imperial units and so forth, but the units, I think, can also help us understand the equations, so that's why I'm putting them in every place. Once we have the desired acceleration, we use Newton's law to compute a desired force that must be produced at the road surface. So I've got a tire on the road, and there's some kind of a force that needs to be applied there. Now it's divided over some number of wheels, I suppose, but the total force that's required. And Newton says force equals mass times acceleration. So I take the desired acceleration from the first step and I multiply by the so-called equivalent mass of the vehicle to get the desired acceleration force. Now in this case, the vehicle is not just a translational motion or rotational motion, it actually combines both of them. And so the people who model vehicle dynamics have described this equivalent mass to combine the actual just resting mass of the vehicle with the rotational mass of everything that's rotating around to get the acceleration force that's required. So this equivalent mass includes the vehicle mass itself plus the rotating equivalent mass. Now, we're designing for an application. I don't know if I've got one passenger in the car or several passengers. I don't know what's in the trunk, if it's empty or if it's full of stuff. So here we're going to design for worst case. So we design for the maximum vehicle mass to get kind of the worst case performance. But of course we could change that mass to see how the vehicle would perform, how the battery system would perform in different scenarios. The rotating equivalent mass takes the motor inertia, which is a kilogram per meter squared item, and it takes the gearbox inertia, also in kilograms per meter squared, and multiplies by n squared. Now n is the gearbox ratio of motor RPM divided by wheel RPM, so it might be like 5 to 1. So n would be 5. And so here I'd be multiplying by 25. The point is that inertias are scaled by this square of the gearbox ratio when they go through a gear change. So the gearbox inertia is measured at the motor side, not on the output side. That's why it combines with the motor here. So that's the input. So I've got your motor, and I've got a gearbox, and then I've got basically the wheels over here, and the gearbox is split between an input side and output side, and I measure the inertia on the input side, the motor side. So that's why it's scaled by n squared. If it happens to be on the output side, I would not multiply by n squared. I'd simply add it to everything else. So we also have number of wheels times wheel inertia to get the spinning equivalent mass of the wheels, and all of that gets divided by the wheel radius, which is how the power gets applied to the road. Now, also, this is a subtle point, a wheel is not perfectly round, neither I suppose is that, but I'm exaggerating. It looks more like this. The wheel is slightly flattened when the vehicle mass is on it, and so we are taking the equivalent radius, the flattened radius of the rolling wheel in this calculation. So it's this distance there. So that gives us our equivalent mass, and that's in kilograms. Now, force equals mass times acceleration. That's the force that the motor is going to provide, except really what I need is the sum of forces equals mass times acceleration. One of the forces is the one that we're providing, but there's also drag forces of different kinds. And so I have to compute those drag forces and subtract them out to get the net force provided or required to achieve the acceleration that we want. So one of the forces acting on the vehicle is an aerodynamic drag, and that's in newtons. And this is a standard calculation. It's 1/2 times the air density times the frontal area, equivalent frontal area of the vehicle, multiplied by a drag coefficient, and then multiplied by velocity squared. So aerodynamic force is proportional to velocity squared, and the constant of proportionality includes a unitless drag coefficient, this equivalent frontal area, which you'd basically end up measuring in a wind tunnel, I believe, for your vehicle, and then the air density at whatever altitude you happen to be driving. Or you could just assume sea level, I suppose, if you wanted to. That's the aerodynamic drag. We also have a rolling drag, so there's a rolling friction coefficient multiplying vehicle mass, multiplying the acceleration of gravity. So it's something times mg, which is the rolling weight of the vehicle. So this is the rolling mass, but when I multiply together, it's the rolling weight, and then there's a friction coefficient multiplying that. And then there's a grade force. If the vehicle is going up a grade, an incline, then gravity itself is going to have an impact that I'm going to have to fight against. So this is mass times acceleration due to gravity. So again, mg, it's the vehicle weight, times the sine of the grade angle. So the cosine is, it's the sine of the grade angle is going to be the one that is the problem. And finally, there's brake drag. And this is kind of a fudge factor. And so for different types of brakes, I might have disc brakes or pad brakes or something, but the pad may be rubbing on the drum, or the disc may be rubbing on the drum, or there may be some other frictional loss that's a constant loss. We wrap that all together into this brake drag. And all of these together then are forces that have to be overcome in order to make the vehicle accelerate at all. And then I have to overcome them by a certain amount in order to make it accelerate at the desired amount. The rolling force here is computed to be 0 if the prior actual speed is 0. If I'm not actually rolling, it's only when I'm rolling that there is this frictional force in the model. So now we can compute the demanded torque at the motor. So the demanded torque is the desired force that I have to be able to produce to accelerate the desired amount, but I also have to overcome the aerodynamic force and the rolling force and the grade force and the brake drag, and there should be a Newton there. And the brake drag, by the way, is multiplied by a wheel radius, all divided by, all of them are multiplied by the wheel radius. There's a bracket here I missed. All of those forces get turned into a torque. We know torque equals force times distance, and there's my wheel, and the torque is at the center, the force is at the edge of the wheel, and so the d is my wheel radius, and the n is helpful because I've got a gear down ratio. So if it's 5 to 1, then I have to produce 1/5 the torque, and so forth. So that's how we get the demanded motor torque. This is how much torque we want. Now, can we get it? The motor specification is going to put limits on the maximum torque that we can achieve. And so we have to compare the demanded torque with the available maximum torque, and we have to take the minimum in an unsigned sense of those two values. And we base the available torque on a model of an ideal three-phase AC induction motor, and that's what we looked at in the last section with a picture. When positive torque or positive acceleration is demanded, we do this calculation. We say if the prior actual motor speed is less than the rated motor speed, then the maximum available torque is the maximum rated available torque. So you remember the torque versus RPM characteristic looked like this. We're saying if I'm operating in this regime, I have a constant torque that is my maximum value. Otherwise, if I'm operating in this regime here, then I have a constant power curve, and the maximum available torque is computed as the rated torque times the motor speed divided by prior actual motor speed. When negative torque or deceleration is demanded, the torque demand is split between friction brakes and the motor. In the electric vehicle, we can actually use the motor to do some of the braking, and the advantage is we can recover energy that way and recharge the battery pack. I'm not wasting all of the energy in heat generated by friction. So energy recovered from the motor is going to replace energy depleted from the battery, but there's going to be some inefficiency, so there's going to be some losses, but it's still going to be better. And this is called a regeneration or regen event. So when we talk about regen, we're talking about putting energy back in the battery pack when we're coasting or braking, basically whenever negative torque is demanded at the motor. So the maximum motor torque available for regen is calculated as the minimum of the maximum available torque for acceleration and a regen fraction times the rated maximum available torque. The limited torque is the lesser of the two in an unsigned sense. And now either way, if I'm accelerating or decelerating, I have a available motor torque. Now that we have the motor torque, we compute the actual acceleration force that's available, and then using that, the actual velocity. So the actual acceleration torque is the computes the actual acceleration force like this. It's equal to the motor torque times n divided by wheel radius. That was the we computed a desired value of this, but we've now limited it, and we've rearranged the equation to solve for the actual acceleration. But I have to subtract out the losses due to aerodynamics and rolling and grade. The actual acceleration is the actual acceleration force divided by the equivalent mass. Now the actual acceleration just calculated might cause the motor to spin at a higher velocity than it's rated for. So we can't simply compute actual speed as actual speed equals prior speed plus actual acceleration times 1 second. Instead, we must compute the motor RPM first and limit that RPM and then compute the actual speed. So we make a test speed, and the test speed equals the prior actual speed plus the actual acceleration, which is this, same equation, but we're checking it first. And then we're making the test motor speed, and that gives us the test speed times the gearbox ratio, and then a conversion factor to turn that from radians per second into RPM. And the motor speed is limited by the maximum rated motor speed, and that gives us then the actual vehicle speed is the limited motor speed, again converted from RPM to radians per second, and by the gearbox ratio. So what we've been able to look at in this section is everything in this black, the thick black line box here. We've started with desired speed. We've computed desired acceleration, desired road force, desired torque. Then we started applying limits. We applied torque limits. We computed the actual force. We applied RPM limits, and we were able to compute the actual speed. All of this assumes that the battery is always able to supply everything we need. This is not going to be the case in practice, but that's the assumption that we make in this code. And if you wanted to have a more sophisticated model, you would also put in battery limits as well. And those should be fairly straightforward if you understand how to simulate a battery and how to simulate this vehicle. Next section, we're going to look at these parts here, how to use the simulation to compute vehicle range, which is perhaps what you are after, because probably you wanted to design a battery pack to achieve a certain required or specified vehicle range, and were you able to do it or not? We get to find out.